Okay.
Welcome to the 5th of 8 sessions in this Agile MBSE Lunch and Learn series. This one focusing on model-based ICDs. Greetings, I am your host, Bob Perro. I am on the board of the NCOSE Chicagoland chapter. The 6 NCOSE chapters that are collaborating on this Lunch and Learn series extend thanks to the series sponsor, Smith and Nephew. And the NCOSE Chicagoland chapter is also sponsoring this particular session. Okay, slide's not advancing. Okay, there we go. So I mentioned that this is the 5th of 8 Lunch and Learn sessions. The first 2 sessions focused on the introduction to Agile modeling. The second 2 focused on improving requirements in an Agile context and with use cases. Recordings of those earlier sessions are available. There's a URL just below the main image on this slide, and it ends up in Lunch Learn 1. And if you just click on that URL, that'll get you to session 1. If you change the 1 in that URL to 2, that'll get you to session 2, and so on. And I also want to point out that the 6th session, which is the next session, is going to be held on December 15th. And that, I know the image says it's proposed, but just before we started this meeting, we solidified that. Okay, I want to mention the upcoming NCOSE GLNC conference the first week in December. It's a hybrid event having in-person and virtual access. Registration is open for in-person attendance now, which also includes virtual access. The registration link appears in the upper right portion of the slide. Registration for virtual only attendance opens tomorrow. The instructor for this Lunch and Learn series, Bruce Douglas, is also contributing content to the GLNC conference. And he's contributing the keynote on December 2nd, enabling digital engineering and MBSE, 2 hands-on workshops on December 1st, scenario-based use case analysis in Cameo Magic Draw, 90 minutes, and test-driven modeling with state machines in Cameo Magic Draw, 3 hours. Bruce is also participating in a panel discussion on December 2nd, accelerating innovation with MBSE and digital engineering. I'd like to also announce that there's going to be a follow-on MBSE challenge, which takes the activities of this Lunch and Learn series and related GLNC conference activities and continues them on for quite a period of time. And the sign up for that begins in December. NCOSE is the world's leading professional engineering organization focused on systems engineering and related areas. It has an amazing array of resources and products, most of which are free to members. For me, networking is the biggest benefit. There are 3 global sectors across NCOSE. The Americas are in sector 1, which is our sector. 6 of the 12 NCOSE Great Lakes North Central Region chapters are collaborating on this Lunch and Learn series. NCOSE has a corporate advisory board. CAB members steer NCOSE direction, products, and content. CAB spans industry, government, and academia. Employees of CAB companies can register as an associate NCOSE member, which gets access to some membership benefits. NCOSE has quite a number of working groups. Working groups are focus areas under the umbrella of system engineering. A few closely associated working groups with Agile MBSE are highlighted in red. So there's the Agile Systems and System Engineering Working Group, Digital Engineering Information Exchange Working Group, MBSE Initiative Working Group, MBSE Patterns Working Group, and Tools Integration and Model Lifecycle Management Working Group. You can find out more information about NCOSE, including how to join as a member, by going to ncose.org. In the last session, session 4, the book drawing winner was Ron Phipps. Congratulations, Ron. Another random drawing will be held at the end of today's session. So I'd like to introduce today's session instructor. Bruce Douglas is a renowned expert on UML, SysML, embedded systems, systems engineering, model-driven development, and agile MBSE. He has written 20 books on those topics. Please join me in welcoming Bruce Douglas.
Thanks, Bob. Let me switch to my presentation. There we are. So welcome, friends. Today's talk is going to be on model-based interface control documents, although I don't like the word document so much, it's in common use, so we'll just continue to use it. I want to point out that not only is there a URL that Bob posted before, you can also go to YouTube and get the videos for these, as well as a bunch of other videos I put together on my YouTube channel. So just go to YouTube and search for Bruce Douglas, and you'll find my channel. And there's like a couple of dozen videos in various topics that's of interest. Talk will be on interfaces and how to specify them, how to capture them, how to summarize them, so you can create interface documents for communication and for other uses. This will be a bit more technical than the other classes I've given so far in this lunch and learn series. So just be aware. We'll be talking a bit more about the techniques and the SysML innards to achieve that. So first of all, what do we mean by an ICD? If you go to Wikipedia, interface control document is in systems and software, provides a record of the interface information, which includes things like services, flows, data schema, and metadata. And we'll talk about all those aspects collected together to understand how a system interacts with other systems or how a group of systems interact. That's what an interface control document captures. So an ICD shouldn't be a design document in the sense that it doesn't go into the internal structure of the system and how does that service realized in the internal design, but rather focuses on how do I invoke services. So it's perfectly reasonable to say, here's a service, this is what it produces, but you don't want to go into how it produces it. That's really not kind of the focus here. Certainly in design documentation, that's completely relevant, but it's not what you particularly put into an ICD. So you want to create all of this information. And the idea here in MBSE and model-based engineering in general is that the model serves as the source of truth. The traditional approach to produce an ICD is you put a junior engineer in a corner with the actual design information, and they produce another document which is a siloed set of information copied from other places, but not dynamically connected to them in any really formal way. And so there's an opportunity for error, and certainly it's time consuming. If only you had a place where all this information was captured and you could directly produce this information in consumable forms. Well, that's what we're going to talk about today. How do I produce this information from that model, which is the single source of truth for the engineering information for your system? So what should they contain? So I've come up with a little list here. So first of all, you have the connection to connection points. So in SysML, connection points are ports. And you don't need to have ports in SysML, but they are handy in system engineering because they make interfaces first-order citizens of your model. And they bring them to the fore so that you can capture them, reason about them, expose them, and deal with them. So these connections are then typed by interfaces of some kind. And there are two primary categories of things in the interfaces. There are service specifications. You want to invoke a service, and these can be invoked synchronously or asynchronously. So they can be operation calls, or they can be send signals around. And these can carry information as properties or parameters of those operation invocations or the signal receptions. They have a service direction. In proxy ports, as we'll talk about in a little bit of detail, this can be provided, required, or kind of provided, required. In addition to that, the service itself has properties. So there's certainly a description of what it does. Why would you invoke it in the first place? Well, because it's going to do this for you. But also, what are the parameters? So you want to have the named parameters, which are values passed in or passed out, or possibly both, to part of that service invocation. So you need a direction, and you also need to have a definition of the information or flow. What is it? And that's part of what we call a data schema. We'll talk a little bit about data schemas today. And you also want to have constraints and other kinds of metadata. For example, you could only invoke the service after the system is in this state or this predecessor action has occurred and completed. There's some constraints around its use, and you should be explicit about those. So there's service specification, and then there's flow specifications. Flow specifications are flows that occur that don't involve the invocation of services. So if I turn on a faucet into a tub, water flows in. Well, certainly, sending the signal, open the valve, is an event. It's discrete. I can invoke a service. But once that service is invoked, water flows, independent of any other services. Water just flows. So fluid flow, energy flow, mass flow, material flow, those are often captured as flows. And they have flow properties in SysML to do that, and they're represented by your data schema as well. The data schema itself contains your type model and all the metadata associated with the type model, and we will talk about that towards the end of this really brief discussion. So that's what I expect in principle to see in my ICD. The connection points, the players involved, the interfaces being supported by those connection points. And in those interfaces, service specifications, flow specifications, and the definition of the things being passed around and constraints and metadata. Now, these interfaces can be done in at least two ways, and sometimes people think about this in three ways. Logical interfaces specify the logical characteristics. So if I have a radar into my nav system, and I want to get information, I can say, please send me the radar tracking information for this thing I'm tracking. Okay, and it sends back information about maybe its combat ID, its position in 3 dimensions, its velocity in 3 dimensions, acceleration in 3 dimensions, other kinds of information. And for that information, I get characteristics of it. But I don't really care about necessarily what does it look like in terms of bits on a wire. What bits come first? Is it big Indian, little Indian, scaled integer format? Do I use the IEEE real formats? That's not part of the logical interface. It's logical properties. It carries this information. It's in this range. It has this level of fidelity and accuracy. That's what I call logical information. And that can be modeled as logical interfaces where you ignore the physical characteristics. The physical interface takes that information and adds additional format information, representation information. Oh, well, that's going to be a scaled 16-bit integer, or that's going to be in 3 bits, and these values mean this. So that specific representation, physical representation, is added to the physical interface notion as well. And you can do ICDs on either logical or physical interfaces. Now, to do that, to really understand how to model these in SysML, really requires an understanding of ports. And this is the place, and I teach a lot, and this is a place where a lot of people have some confusion. It's easy, and it's a little bit complicated, so it makes sense. So we're going to go through a little bit about ports in this discussion. So in SysML, you have the notion of a collaboration. Collaboration is a group of object roles working together. Object roles in SysML are called parts, working together to achieve some larger scale purpose, right? And there are two primary ways you can build these collaborations. One is you can build them together by type. And if you're doing that by type, you connect to a block, which is a type of thing. And the block can be subtypes, you can aggregate other types, but it's a type architecture to connect and run the collaboration. An alternative approach is to connect by interface compliance. I can connect anything here, regardless of its type, as long as it complies with the interface. So that's a different, somewhat more general means in SysML to create collaborations. And to do that, you use ports. And as I mentioned before, ports bring interfaces to the fore and make them kind of first order citizens. So ports are named connection points that enable collaborations and make interfaces explicit. There are 4 kinds of ports in SysML. We will only talk about proxy ports here because that's the most commonly used right now. They're introduced in SysML 1.3. And so here we just see a quick example. We've got a block here, an engine with ports, and we see it has some properties like some values and signal receptions and operations. And here we've got these ports, these little boxes on the edge. These are these named connection points. We have one we connect to the exhaust system, one to the drivetrain, one to the ignition, and one to the fuel tank. And you see the stereotype proxy indicates that it's a proxy port. Let me open up another window here. I'm running this on 2 machines. Okay, so here's an example of some use of ports. So with the ports, we've got parts inside, in this case, the NVIDIA part and the ACES part. These are typed by blocks. You see the blocks down below. These are the blocks that type those things. This is called the structured compartments of the computer block. And in it, we show these parts, the graphics card type part and the motherboard type part. Then we've got, I should mention really quickly here that these are overall on the right-hand side, the other left, right-hand side, we've got interface blocks. And these would be where we type the port information that goes across the port. So interface blocks for proxy ports. There's a property of ports called isBehavioral. Where this is true, we call those behavioral ports. Where it's not true, we call those delegation ports. So if a computer gets a message that it wants on this port, and this is a delegation port, that message will be passed on to this behavioral port for processing. And the behavioral port is one that provides the service that's going to be invoked. And this just delegates it on. And this provides encapsulation, hides internal parts. The client of this information can't see what's inside the computer. It just knows I can invoke this service on this port. So isBehavioral is the thing. These are connected. The ports are connected via what are called connectors. Now, connectors can't be used to connect types ports on blocks, but they can be used to connect parts, which are roles that instances play, typed by those blocks, right? So here we've got this part named NVIDIA, and I can show the connection here between this part and this part on the block with a connector. But between 2 blocks, I can't draw a connector between 2 blocks or parts on a block. It's just not allowed. And there are technical reasons why. If you want to know, you can read this back. With proxy ports, interfaces have a perspective. And that perspective is either unconjugated or conjugated. And conjugation is indicated with the little tilde character here, shown here. Tilde iKeyboard. This is the conjugated port. What conjugation does is reverses the directionality of the service. So if the service here is provided, you always read the directionality from the unconjugated side. So if a service is provided, that means it's required on the conjugated side. And if a service is indicated as required in the interface block, that means on the conjugated side, it is provided. So provided required. So it's the basically reverses the directionality. That's kind of the point. I think I might have said that wrong. So if it's a provided service in the interface blocks, the conjugated side requires it. If it's required on the in the interface block, if it's required, then the conjugated side provides it. So it's always the reverse, right? Which is why it's confusing. So let's look at a quick example here. We've got a sensor block, we've got an actuator block, and we've got things we're going to use to connect them, these ports. So we've got P actuator and we've got P sensor. So P sensor is this port on the actuator where I'm going to connect to the sensor. And we see its type is I actuator sensor. And it's compatible with this other port here on the actuator called P actuator, on the sensor rather called P actuator, because it's the same type interface, but one side is conjugated and the other side is unconjugated. And that's how you can tell they're compatible. So a little bit about naming conventions. This is a really common thing that I do and I found helpful for people because it clarifies. It's easy to get confused. So for port names, a pretty common convention I'll use is a lowercase p followed by the name of the block I'm going to connect to. It's going to be a part of this type. So P actuator means the sensor here is going to connect to something, an instance, a part of made from actuator. And P sensor means that this actuator is going to connect at this point to something of type sensor, a part of the type sensor. So that's the naming convention for the port. For the interface block, it's really easy to get confused. So what I do is that lowercase I, followed by the name of the unconjugated side, underscore name of the conjugated side. So here we've got P sensor, and the interface block is named I actuator sensor. So actuator is the unconjugated side, sensor is the conjugated side. And so when I look at the interface block, I can immediately see which thing is providing it, which thing is requiring it. I can tell that from the naming convention. And in my experience, that really simplifies things. So otherwise, it's just so easy to get confused. Okay, so ports, again, I mentioned before, ports are optional. But if you want to use ports, really you only need proxy ports. There are three other kinds of ports. I'm not even going to mention those. Now, proxy ports are typed by what are called interface blocks, which are not the same kind of meta class, same kind of thing as interfaces. But we use interface blocks for basically the same purpose, but they're a little bit more flexible. Interface blocks can show both service invocations, synchronous and asynchronous, and flow specifications, flow properties. So we look on this interface block, I actuator sensor, you see there's a flow property called value, and it has a direction, in. So perspective is from the unconjugated side. That means that actuator has a flow property named value, and it has an indirection. The sensor has a flow property named value, and it's going to have the direction of out because it reverses directionality when you conjugate the interface. Okay, we'll see an example on the next slide. There's an operation which you can invoke is required. That means that the actuator requires sensor to provide get value. And there's a provided signal reception, EV sensor status, a naming command, EV for event. That's just a Bruceism, something that I do. So here we got sensor status. Now what that means is that the actuator probably has a state machine, although it could be an activity diagram, but it has behavior that receives this event, the signal, and then does some service based on that. This is like you're going to pass in a value called status, which is just in this case, just a number. That means that the actuator might have a state machine that receives that event and then acts on it. And the sensor is the one who's going to send that signal. So providing the signal reception means that the sensor will send it and the actuator will receive it. So flow properties are in, out, or in-out. Services can be provided, required, or provided required. And this provided required is pretty rare, frankly, but the provided required are pretty common. So a single interface block can have things going in multiple directions. Some can be provided, some can be required, some can be in, some can be out in the same interface block. And conjugation reverses the directionality of all of those features of the interface block. Now, I don't use flow properties for software because in software, it's always invocation of services that you're passing data as a part of calling an operation or something. You don't flow data just doesn't flow in standard languages like C or Python or C++ or Ada. You invoke a service, you call a behavior, invoke a behavior. But for some middlewares like DDS, which is data centric, I might do flow properties just because it maps pretty closely to the topics in DDS. But in systems engineering, I use this to represent flows that are not tied to specific behavioral invocations. So as I mentioned before, energy flow, fluid flow, mass flow, all represented as flow properties because the energy is flowing over some period of time, well, something is true. But for invocation, discrete thing, at this point, I'm going to send a signal, or I'm going to invoke an operation. I use services of some kind, either synchronous, I use operations, or asynchronous, I use signals. Your mileage may vary, which you want to do. So service invocations in the interface block have to be stereotypes with a stereotype called directed feature, and that adds these properties called feature direction, which is provided, required, or provided required. You don't need to add the directed feature to flow properties because, well, it's in their nature of flow properties to flow. So you get the kind of in, out, or in, out already. But for services, they don't get that. You have to add it by adding the stereotype. The directionality of the feature is always read from the unconjugated side. I'm hitting this pretty hard because it is a common point of failure for people modeling is that they get confused. So here we got interface block, I, controller, sensor. So again, the controller is the unconjugated side, sensor is the conjugated side. And we've got value, we've got some required operations. And that means that sensor will provide those because that's the conjugated side. And controller will require those. Signal receptions, we've got some required. And that means that the sensor will create these and send them to the controller because this is over a port, right? And for the provided interfaces for services and signals like here's a value or sensor status, it will receive that signal and then do something based on it. So what does that look like? Now here we've got the sensor and actuator blocks. I've highlighted just the ports that are used to connect these in the IBD, internal block diagram. And this is the type of the interface block, the type of the ports here. So for the in property, here we see then the actuator side is in fact in because you always read from the perspective of the unconjugated side. And for the sensor, we see it's out. Now, in actual fact, they don't necessarily have to have the same name, but I'm not going to go into the details of how to do that in this brief introduction. So for now, I'll just use the same name and call it good. For required, that means it's going to be provided by the sensor. So here it is right there. The sensor provides an implementation method for the get value operation because it's a required service across this port. And then for the provided EV sensor status, that's a signal reception. That means that the sensor will somehow as a behavior to create that signal and send it across this port to here to the actuator, and the actuator will then receive it and then do something on it. Right, so that's how it works. So some recommendations for modeling the interfaces in SysML. I only use proxy ports and I type them interface blocks. So there are other means you can do this, but multiple means just means you're cutting out work for yourself. And proxy ports are almost always completely adequate for defining interfaces. So I recommend just use those. Then I'll elaborate the interface blocks, these connection points, with the things that flow, either inflow properties or the service invocations, synchronous or asynchronous. In my interface blocks, you should stereotype those as directed features to get the feature direction property that you can set. And then you can use those properties to set the direction of the features. So that's defining the data in the model. Then you want to create views of these things to visualize them and to expose them to the stakeholders. And you'll use interface diagrams, which are a usage of a block definition diagram. I'll show you what that looks like. And then you create tables and matrices to expose the data. And then you can export these views and the related model information into reports to create your ICD, which you're going to share with the stakeholders, who may not be on Cameo or be Cameo literate or model, whatever modeling tool you use. For this presentation, I use primarily Cameo, although I do show you how to do some cases in Rhapsody. But you can always, whatever modeling tool. I don't mean to push Cameo particularly. It's just the one I use mostly for this slide deck. So here's what I mean by interface diagram. In this particular case, I used standard ports just to show you what they look like. We've got lollipops for provided services and the socket here for required services. It's done a little bit differently than interface blocks and for proxy ports. But this is the kind of thing I expect to do. For a subsystem, I show the subsystem with these connection points, and around the periphery, I show the interfaces that are required to talk to it, basically. And if I've got 15 subsystems, I'll have 15 such diagrams, one per subsystem. And this, I find this a very useful kind of view. If you want to know the details of the individual services, yeah, you have to drill into that. But nevertheless, it gives you an overview for this subsystem or the system. How does it connect to other things? How do I build collaborations with other things to do that? So let's do a little bit more detailed example here. So this is going to be done in Cameo model called a room with a view. So here is my BDD, where I've got my Arctic air conditioning system, which has parts. These are roles of these blocks, instances of the blocks play in the running system. There's a panel so I can set values. There's a display so I can see what's going on. There's outside, which is, you can think of as an actor if you want, but in Cameo, actors can't have ports. So I often use blocks for that, which provides, driving force for energy exchange. There's a room I'm trying to control the temperature for, and there's a controller which is doing the work. So these are the parts involved. This is what I call the composition architecture. For the type architecture, I can expose these blocks here with their ports, the interface blocks, which I've colored magenta, so they kind of stick out, and the things that flow. So we've got flow properties, we've got flow properties here, some signal receptions and stuff. So this defines what goes across these connection points. And we see little comments in the corner showing what I call the mission of the diagram, the things it's trying to show. And this is what I call the connected architecture, where we show how these parts connect in the context of the Arctic HTT system, and which I can then execute because now they're connected and I can actually cause stuff to happen. So these three views are pretty common for a system that I might show. There's the composition architecture, how do they fit into the context? There's the details of the types and the ports, interface blocks, which I call the type architecture. And then there's the connected architecture where I actually connect them up on an IBD. So first, you have interface diagrams. Here I've got this is a Cameo feature called interface information. And I've extended it to show the documentation, which is the description associated with the diagram. Pretty common thing that I do because the environments where I work, at the top of the documentation is the classification level. These are all unclassified. And the mission, what am I trying to show? So here we got the controller block. and the interfaces that it exposes. We've got some signal receptions off to the panel. Here we've got a flow off to the display. And here I've got some flows off to the room controller, to the room. And there's one for the room where we see the room block and its interface blocks that are supported by these ports. Now, in a real model, I would have these for every system or subsystem of concern. And then when I generate my report, these are the start of the discussion point for this subsystem. What does it do? What are the interfaces? Blah, blah, blah. This is the starting point of that discussion. And then underneath this, I would detail out what's inside those interface blocks, the data schema supported, and all the other information that's related. So this is a view I personally like. ICD tables. This is a really nice Cameo feature that you can create diagram and make tables. Yeah, tables are diagrams in Cameo. But, the basic type for this table is the connector. The context is the owning block that owns those connectors. In this case, we see the port, we're talking under discussion, the features that go across the port. So this is the features in the interface block that are being passed along there. The item flows, and then on the other end, there's the target port and its features and the part that owns those features. So we see this as a table that shows the interface block, and I can create that with like a single gesture in Cameo. Now, in tools like Rhapsody, you can also create such a table. I haven't done other tools other than Rhapsody for these sorts of things. But with Rhapsody, you kind of have to want it because you'll have to go into what are called context patterns to describe what you want to construct in the table. And context patterns are not well documented, frankly. So you'll have to spend some time, pulling your hair out and figuring out how to do that. With Cameo, you can just, in a single gesture, create that. With Cameo, you have black box view, which is one level deep. So current surface level, at this level of abstraction, for its context, that's what's shown. And if there are internal nested parts inside those parts, they're not exposed. The white box exposes all the detail. The black box does not. So that's the difference. So if you're in the DODAF, that world, this would be like an SV6 or an OV3. If you're not, don't worry about it. Another really nice view to have is what's called the NSquared chart. An NSquared chart shows how things connect. And it's really equivalent to the information that you have on this IBD. So it's a matrix, which is basically a part-by-part matrix, where you show the internal parts of the context and the presence or absence of a connector connecting them up. And this is independent of whether you have ports or not. Okay, but I can show how these connect up. In Cameo, you just say it's dependency matrix, which is a little bit misleading because a connector is not a kind of dependency, but fine. It's a relationship matrix, really. And you can show how they connect up. Now, in this case, it's pretty straightforward, pretty simple IBD, pretty simple matrix. And this corresponds to an SV3 if you're into DODAF. But in more complex systems, you get these really large IBDs sometimes, and it's not obvious from there because there's so many parts and so many lines running around doing stuff. And this is a nice summary. So I've also shown a more complex example. This is from an air defense example system. And you show what things connect to other things. And so this is a nice, very nice summary view. One of the things missing from this view is I can't see which interfaces are being invoked. So so the value of this grows as the number of participants grow. As you can see, the NSquared, it's called NSquared matrix for a reason, right? So as you get more and more, the value of the NSquared diagram grows. So I was talking with a person by the name of Sean Ricks at the MITRE Corporation where I work, and he had this solution using color coding. So you can go through and you can add in the dependency criteria a little bit of code snippets to elaborate that. And so here we can show the different kinds of arrows depending upon what interface is being invoked. And one of the style properties is color. So these different interfaces, you can identify different style properties, different colors to show these. So here we're saying the same Arctic AC system, we can expose which interfaces are being shown, but you don't get to see the services. You can still expose those, but at that point, it's going to become pretty cumbersome to read in the table anyway. So yeah, it doesn't expose the individual services, but at least the interfaces are identified. So that can be handy. So thanks, Sean, for creating this for me. You can also create just interface block tables. That it's a table, and the primary elements here are interface blocks. And again, it's pretty easy to do in Cameo. This is actually pretty easy to do also in Rhapsody. So here we see the criteria in the layout. The interface blocks are the primary elements here. And here's the name of the different interface blocks. And we see in the columns tool, you can add different features to add in the columns. In this case, you've just added own members. So interface block has members like flow properties and event receptions. So these are event receptions, and we see the flow property and the direction and the types of these elements for the flow properties. And that's, again, a nice summary view of that interface information. If you want to, you can do it in Rhapsody. So I just want to show you that, yes, you can do that. To do that, you do a table layout, which is a separate element in Rhapsody where it's kind of combined in Cameo. And you identify what you want to show as the columns of this table. And you define the property in advanced options. You go and you add in the context pattern for what defines what shows up in the various columns. I'm not going to go into that as a Rhapsody specific feature, but here we have something very similar where we've got, let's take ACES control surface. So here we've got the interface block, ACES management, ACES control surface. So this is the interface between the management system and the actual control surface on the aircraft. And there are a bunch of things. There's the signal command to position, and this signal has two different arguments. It passes in an ID and a position. The ID is a sort of type surface ID, and the position is of type integer. If you look at update position here, here we got again a signal reception for called update position, and it has three parameters: ID of type surface ID, movement duration of type second. So here we've added units here. The second comes from the SysML type library, or just the units library. And then position, again, in terms of an integer. So we can characterize the interface blocks, the flows and services and operations and signal receptions and stuff in there, and the arguments that they're carrying and their types in a table. And it's defined in terms of this context pattern down here. So the information you pass should be part of your data schema. So I talked about things like, service ID and position, and some of these things can be complex. So here we've got a typical data schema. So we've got a flight property set for my aircraft. A flight plan is a collection of flight property sets. Some of the points in this are waypoints. That's the Boolean here. And each flight property set has attitude, which you see is a block because it has roll, pitch, and yaw, which are again typed by attitude angles. In this case, for attitude velocity, we've got the rate of change. So we've got D roll, D pitch, D, first derivative in time, right? And then for attitudinal acceleration, we've got D squared. You got a second derivative of roll, pitch, and yaw. And then we've got position, altitude, latitude, longitude, where altitude is height in meters, latitude is degrees meridian, and longitude is degrees meridian. And then you've got velocity, which is the first derivative of those, and acceleration, which is second derivative of those. And the flight property set also has a measurement time. So at what point in time did this measurement occur? Right? So that forms a flight property set. A flight plan is a collection of flight property sets, right? We can also represent this in tabular form by having value property table being the main things. This is again Cameo. And we see the acceleration here it's the owner. So the main thing, the element is a value property, like D2 altitude, D2 latitude, and so on. And the first column, though, is the owner of that. And the third column is its type. So we've got the data schema shown out as in tabular form, as well as in diagrammatic form. You can do the same sort of thing in Rhapsody. So here we've got a different data schema for different, this is actually for attitude control system within an aircraft, where we've got something like control area surface for surface position. We've got properties like surface position, measured position, a low and a high value, the acceptable range, commanded position, you got measured position, commanded position, and how long it took you to achieve that. So you keep track of that for stability of the aircraft. And you've got other properties here, and you can expose those in a table as well. So here we've got the type, the name within that type of the data schema, and its type, the type of that element. So date time is a date time type, error is of error type, which is a block. It might be, actually it's a enumerated type. We take it back to the enumerated type. Surface ID is another enumerated type. Pressure is in type of pascals. So you can expose that in your data schema table. Metadata. Okay, so metadata is data about your data. So we've got types, and that's good, but that's not enough. So if I have position of my rudder, let's suppose it's a type integer. I can't just give any value to it. Really, it's only valid in a certain range. So we have the notion of a range, which is formally called an extent. So what's the low end or what's the high end of a continuous range? Or there might be ordinal discrete values. You can have the value 6 or 10 or 25. It could be discrete ordinal values, or it can be a continuous range. But that's, what is the set of acceptable values for this thing? If I say integer, say suppose I'm doing reals and it's to model the weight of a patient for medical system. Well, it shouldn't be 0. It shouldn't be negative. If it's the weight of a person, if it's in kilograms, it shouldn't be in the range of thousands, right? You know, it has a constrained range. So this is specifying that metadata about what is the constraint on the range. Okay. Not the only way to do it, but it's a way to do it. Then we have the notion of precision, which is the amount of detail with which something is represented. For scalar numeric values, you can think of number of digits of precision if you want. A reasonable way to think of it. Accuracy is the conformance to that precision. And normally think about a plus or minus, plus or minus 0.1 or 0.2 or 0.10, 0.001, whatever is relevant. It's a degree of conformance, or known as the precision of an output. Fidelity is the precision of an input. How closely can you specify an input? So precision might be 0.1, fidelity might be 0.5. We can only specify it, within 0.5. But precision, once you have the output, it's to that range. So I can only specify my rudder plus or minus half a degree. But when I control to it, it's 0.1 degrees is my accuracy of my output. So those should be modeled and represented. Timeliness, things like lag and worst case execution time and average performance time, that's important information because you're building systems that have to operate in the real world. And if your control law is applied without regard to latency, it becomes unstable very quickly. Performance, capacity, lag, bandwidth, capacity, throughput, stuff like that. Synchronicity, whether it's guarded or unguarded, you have a semaphore with blocking, unblocking, all the stuff around that can be represented, and as well as flow control can sometimes also be represented. Only after this is an acknowledgement or a negative acknowledgement, modeling all that stuff. And how do you add metadata? Well, there's a few ways. What I typically do is I add a stereotype. In this case, we have a stereotype called constrained subrange, where I have digits of precision as an unlimited naturals, which is basically natural numbers, 0 or more, but they're integers. Accuracy is usually a plus or minus 0.01, 0.001, something like that. And fidelity also is usually a plus or minus. And then the low end and the higher end, that's where I'm specifying a continuous range. That's why it's continuous subrange is the name of the stereotype. So these are attributes of the stereotype. When I apply the stereotype to a value property, they become tags, which I can fill out for that particular value property. So my robot arm, I've got joint angle, where I've applied the stereotype constrained subrange, is of type planar angle in radians. And we see 6 digits of precision, accuracy of 0.01, fidelity of 0.05, from 0 to 2 pi is the range, right? So that's what we call metadata. It's data about the information of joint angle. We got the type and the various metadata. And this is important to specify in your interface control documents, because if it's degrees, it means something entirely different than if it's radians. And if it's, if minus 35 is out of range, you need to know that, right? So metadata. So let's do an example with metadata. So here's our same example before, where we've got our units and our values associated with the value properties. And we've got our stereotype. In this case, I've called it qualified. So in Rhapsody tool, there's a profile called the Harmony System Engineering Profile. And the qualified stereotype, a little bit more elaborate than this, but it's basically included as a part of that profile. So I added that into the Rhapsody tool, along with anti-lapping. We added that into the profile for the system engineering profile for Rhapsody. But it's not hard to add. And then you can build a table, which includes not only the data, but also the metadata. So here we've got our value properties, just like we had before, with our owner. The acceleration owns second derivative of altitude, for example. It owns, second derivative of roll, pitch, and yaw. It has roll, pitch, and yaw as the attributes of the altitude, the attitude part property of the value property set. Here are the types involved. And then here are the metadata. So for altitudinal acceleration, minus 10 to plus 10 is the range acceptable. The accuracy is 0.05 and the fidelity is 0.05. For velocity, linear velocity, so along the direction of movement, the low value is 0 to 3,000, and the unit is kilometers per hour, and velocity, and the accuracy is 1 and the fidelity is 1. So capture the metadata. So in summary then, that's how you capture information and then you produce a report. I didn't want to get into report generation because of, well, lack of time, basically. We've used up our hour. The nice thing about using SysML specified information that goes directly in your ICDs, it's drawn from your source of truth, your design source of truth. And then you produce a report. Now, reports are normally typed by templates that, and then the report generator then walks over your model, pulls data out to populate the stuff you've defined in your report, and then you get a report. In this case, the report would be your ICD. Because it's based on templates and modeling guidelines, it's easy to enforce the information content structure on your report to meet your needs. And it's very, very flexible. You can create different kinds of reports for different purposes, for different stakeholders, but it's all drawn from the source of truth and requires little or no human intervention. Once you've got it set up, you generate the report. There may be some fix-up because you might want to go find information from other sources, or you might want to add additional textual descriptions, which for some reason aren't in the model. I'd recommend you put the model, but for some reason they're not. There might be some touch-up that you want to have. But it's very easy to do and very low effort once you've got it set up. And the format of the information is very flexible. You can have diagrammatic form, tabular form, matrix form, and you all include that in your reports. So that's a very kind of easy way to generate this ICD. And that's how you can use SysML to represent information to produce your ICDs. If you want to know more, I've got stuff on my website. I've written about this information in my books. I've got the YouTube channel. I mentioned that before at the start. You can find some videos on that. With that, I'll give control back to Bob or to Jack from there. So thank you very much.
Thank you, Bruce. What I would like to announce the winner for the book drawing. The book drawing winner is Paul Miller from the Three Rivers chapter in Pittsburgh. So congratulations to you, Paul. And we'll be coordinating.
I'm absolutely delighted. And I have the first edition of Real-Time UML, and this will go right next to it. So thank you.
Very cool. So we'll coordinate with you on your address, and we'll get the book out to you.
Sure.
Okay.
Thank you. Thanks, Bruce.
You're very welcome.
And so we're going to enter the Q&A period now. And so let's start with Dan Carlock. His question is on page 12. Could the outside block also be related to Arctic AC system via a reference association?
All right, so let's go back to page 12. Slides 12 here. So the short answer is, yeah, sure. This is just a particular architecture. So normally, when you create what's called compositional architecture, you have a context that contains parts that are typed by the blocks of things in the context. And then you build up this IBD to show what we call the connected architecture. So a reference property is where instead of a part property, or instead of a composition, you have an association. So that's why we have you have a reference property. And so yeah, you could do that, but still there has to be some context where that's a part to create an IBD so they can actually exchange information. You have to create the instances somewhere. And this is just a convenient way to create the instances that run in the context. But sure, yeah, reference properties are fine.
Okay, thanks. Our next question is from Christopher Carhart. How can you use the ICD table to identify / track the true end / origin of a signal through a connector chain across a multi-tier compositional hierarchy?
Okay, so we had an example. Well, here, actually, this one right here. So we had this white box ICD. That's basically what you want, so that a part will contain a port, and inside the port, then we have specific properties. And given the directionality, you can see where its source is and where its target is. So because this is a required service, that means that somebody else will have to receive that from this perspective, right? Somebody else will have to receive that and act on it. And so the source of the signal in this case will be the part that has it as a required property, because that's going to create the signal and then send it off to somebody to require somebody else to handle the signal reception. So if it's particularly for signal receptions, we do that. Now for depth in multiple layers, that's what the white box ICD is about. It'll show multiple layers of nesting. That's what that's the white part of the white box perspective. So you can track it down through there. You can also expose this in a behavior on a sequence diagram, animate sequence diagram from the execution. You see it created and being on a sequence diagram. Another common way to visualize an execution. But in terms of your ICD, this is, I think, probably the best way to visualize that. Or you can create a particular view. If that's particularly important, you can create an IBD with where the parts have a structured compartment and show that part on the same IBD because that's a particularly important path that you want to expose. So there's a few ways, but probably the most common way would be this kind of a table.
Thanks, Bruce. Next question is from MT Malon at Raytheon.com. Early slide indicated ICD either logical or physical. How do you
Yes.
create, link, and communicate both views?
Well, they're really kind of different models. So when I talk actually in this December 15th, not to like, hark for that, December 10th and 15th, we'll talk about the handoff. Part of most of system engineering, in my experience, right? Most of system engineering is done with a logical perspective. Once you start handing off the downstream engineering, they're going to build actual systems or actual subsystems that have to meet actual physical interfaces. So that point in the process, it becomes important to have the physical realization. To cut ahead to that discussion, we take the logical interface specification and we create a physical realization of it. But they're really different models. In the logical model, it might be an event reception. In the physical model, it might be a 1553 bus message that'll represent that in the physical schema. So they're basically, you apply this, but now to the physical model. So logical and physical model are normally discrete models. And even if it's in the same Cameo project, they form, to my mind, different models. One is the logical perspective model, and one is the physical perspective models. And you would create the ICD view on the different models. So I hope that answers your question.
Okay, thanks. Next question is from Abteen Najan. Maybe I missed it during Bruce's presentation, but how do you practically build an N2 diagram, N-squared diagram? Thank you.
Okay, so let's go to the N-squared diagram. That was here. You basically, in Cameo, now it's a different set of gestures in Rhapsody or some other tool, right? You create a dependency matrix. And so you right click, create new diagram, and that's where matrices are. So you'd have to select dependency matrix. Then you add part property as the row and column element metatypes. The scope is whatever package where these are represented. It could be the entire model, but in this case, it's just a package of these things are in. And the criteria is you want connectors, because that's the thing that are connecting up the parts on the IBD. And that's basically how you do it. I hope that answers your question. And of course, the specific gestures will be tool dependent.
Thanks, Bruce. Next question is how to include thermal interface information in the ICD. That's from Eric.
So thermal information. Okay, so the fact that it's a thermal interface, to my mind, means there's energy exchange. So you'll have flow properties modeling energy exchange. And it could be heat, it could be temperature, whatever thermal properties you're trying to exchange, those become flow properties. And as flow properties, they are then populated in your interface blocks. Then they show up in your interface tables because they're flow properties. So that's how I do that.
Okay, thanks. Christopher Carhart has another question. When do you use item flows? I noticed that, excuse me, I noticed that column is blank in your ICD table.
The short answer is, since you said you, that meaning Bruce never does that. Bruce hates the item flows. But they're not like they're terrible, but it's just the thing I don't like about item flows is they really go back to 1970s data flow diagrams. And I don't like data flow diagrams because they don't have enough information for me to really process the work. I really need to know sequencing. And item flows don't play into a sequence, whereas operations do. They do play into a sequence because I can talk about service invocations with either synchronous or asynchronous messaging. I can talk about this comes this, and then there's state behavior or activity flow behavior. And so that's why I typically don't do those there. Having said that, if you want to do that, you certainly can. Item flows are going to be typed by blocks essentially, and you can type the item flows and they become part of the, so on your connectors, you'll put item flows. Instead of using interface blocks, you'll put item flows on there, on the connectors between those. And then you can characterize those with the data and metadata. So I would say, I would probably, if I was using item flows, I would use them on connectors that realize associations rather than realize ports. Because if I'm using port, I would use flow properties. But if I've got an association, I can add item flows to associations and also to the connectors that realize those associations. So if I was gonna do that, that's how I would do it.
Okay, very good. Let's see, thought that was the last question, but let's see, Jack's sending one here. General question from the registration system. Several mentioned that they are interested in transitioning ICD methods and processes to MBSE. Any suggestions on getting started, tips, do's and don'ts?
That's a whole bit about how do I adopt? How do I adopt the technology of digital engineering? That'll actually be part of the keynote that I give at the meeting in a couple of weeks in Detroit. But you have to think about your adoption strategy. And somewhere in there, moving the interfaces over is part of your digital engineering, your MBSE adoption strategy. And that has to be thought of in terms of what you do now, coming up with a form that you want to do subsequently in your end goal process state, and update it that way. So it's a big topic, but yeah. Is that
Okay.
the question, I hope?
So we got a comment, great overview. Thanks, Bruce. So thank you, Bruce. And Jack, unless you have any other questions, I think we've exhausted our list of questions.
Yeah, we're good.
Okay, very good. Thank you, Bruce. This is a wrap. And we look forward to seeing you all and some of your friends on December 15th for the next session in this Lunch and Learn series. Have a great rest of your holiday weekend.
Thank you, Bob.